Hi, my name is Aidan Gesch, and my project is titled Using Machine Learning to Relate Grain Boundary Properties to SOAP Descriptors. My project director is Dr. Chongze Hu from the Department of Aerospace Engineering and Mechanics. In this presentation, I'm going to start with a brief introduction into what grain boundaries are and some problems with current grain boundary research, then introduce my proposed solution and the methodology for my research, then conclude with my current results and future plans for my project. So, what is a grain boundary? Well, in a crystalline material, a grain is a region of the material in which the lattice of the atoms is perfectly aligned. The grain boundary is the interfacial region between two grains where the lattice is imperfect, where two lattices of different orientations meet. This structure has a large impact on both the local and global properties of the material. At the atomic level, it introduces stress and strain fields, and overall, it changes the strength and ductility of the material. We can model these grain boundaries using coincident site lattice theory. This maximizes the number of overlap atoms between both grains and produces steady yet realistic grain boundaries. So to investigate grain boundaries, we have a variety of tools at the present. Experimental research is performed primarily with electron microscopy. This includes but is not limited to scanning transmission electron microscopy. This allows us to investigate the current position of atoms and the structures they form. In the computational field, which is where my research is, we use atomistic simulations. Two ways we can simulate atoms are with density functional theory and molecular dynamics. The former uses electric potentials to determine the most likely places for atoms to be, and molecular dynamic uses the intermolecular forces to see how atoms move. These can be applied to statistical techniques like Monte Carlo simulations, but they still require atomistic simulations. This leads us to the main problems of the traditional approach. Simulations become exponentially slower the more atoms you introduce. This is because the same equations have to be applied to every atom and every pair of atoms in the structure. This limits the complexity available to be analyzed with traditional means. Additionally, the initialization parameters and the final results are not necessarily directly correlated. This means that atomic structures with similar setups can have very different results, or with very different setups can have similar results. This makes it hard to categorize grain boundaries by their stated properties. So this is my proposed solution, using machine learning to translate between the grain boundary structure and its output properties. This is done by converting the grain boundary structure into an atomic descriptor, which will be described on the next slide. Once we have this atomic descriptor, which is a single vector with a series of key values that represents the atomic state, it can be fed into a physics-informed neural network, or PINN, to predict the output properties with great accuracy. The neural network is trained using a database of previously simulated atomic structures. I'm using a database of about 5,000 grain boundary structures of copper-silver systems, with copper as the main bulk of the structure and a small percentage of silver added. I have CSL grain boundaries at various misorientation angles. So what is this SOAP descriptor I'm speaking of? The SOAP descriptor is a way to describe the environment around an atom without discussing its position or orientation. We start with a central atom and convert the surrounding atoms within a cutoff radius to Gaussian density functions. This height represents the probability that an atom will be at that location. Then we combine the Gaussian distributions with a series of spherical harmonics and radial basis functions. This results in a characteristic vector that uniquely describes the surrounding environment of an atom, but does not change if we translate, rotate, or reflect the atomic structure. This means that it is much better at describing a grain boundary than simple atomic coordinates, which are commonly used. This descriptor can be used in a variety of ways. Here you see a series of 6 images. These are representations of the descriptors of atoms in 6 different grain boundary structures at 3 different temperatures and 2 different percentages of silver. As you can see, the descriptor has different behavior based on if it is near or far to the grain boundary. The dark color is near the grain boundary, where descriptors are very spread out, which indicates a very chaotic structure. The bright colors are far from the grain boundary, and those have much uniform properties. We can also determine that increasing the doping percentage has a much higher effect on the descriptor than increasing the temperature. This matches our established knowledge. We can also use the descriptor for grain boundary region identification. First, we normalize the SOAP vector, which means we set it to be a magnitude of 1 while preserving the angle. This eliminates the knowledge of how tightly packed the atoms are, but preserves the configuration. This is important because this means the results generalize to any type of element, not just the one we're studying. Then, from the unit vectors, we subtract the median value. This means we take away the average vector in the structure, which represents the bulk. This leaves us with a magnitude near 0 of atoms that have structures like the median, but a high magnitude of atoms that have structures that are very different from the median. This results in spikes in the grain boundary region, which we can autonomously identify and label. We can also characterize the grain boundary width based on how wide these spikes are, which is important to grain boundary research. Finally, we can classify grain boundaries based on the SOAP vectors. My research will use machine learning models to translate between a latent representation and real physical characteristics. Traditionally, this is done by performing atomistic simulations and then taking relevant properties like the composition and temperature to make the predictions. This does produce statistically significant predictions. However, the SOAP vector does a much better job than sensible measures. This is because the SOAP vector is not affected by any permutations of the structure, but gets to the underlying atomistic environment. Introducing the SOAP vector in addition to the traditional components results in the best performance. The next steps for my research are combining my methods and expanding them to more systems. Specifically, if we implement grain boundary detection before we choose a single characteristic SOAP vector of a structure, we get a very precise SOAP vector compared to the average SOAP vector across a whole structure. Additionally, a robust hyperparameter search will allow us to optimize the machine learning model for our specific use case instead of using an off-the-shelf model like is implemented currently. Finally, if we are able to expand the training set to include additional grain boundary types or material systems, this will expand the scope of predictions we're able to make. Now I have a few minutes for questions from the audience.
On slide 6, I think I heard you say that the initial training was done from some simulation values. And simulations may be off at times. Is there any check that you do to verify that the model you receive actually is giving the right results from some ground truth checks?
Yes, so this database that I'm using is one that Dr. Hu has been curating over months and years. All of the samples in this database have been investigated and compared to the literature to ensure that they meet our expectations. Additionally, these simulations are governed by the physical rules, and they can't produce a result that we wouldn't be able to observe in real life.
I'm personally curious about how this set of resources, this research, these methods could be applied to structures that aren't grain boundaries. Could you explain a little bit more about that?
Sure. So my specific neural network, once it's trained, will only be applicable to data that is similar to the training set. So my trained network will not be able to make predictions about non-grain boundary structures. However, the workflow that I'm using can be applied to many different situations. Any type of research that uses atomistic simulations can be accelerated by first finding a latent representation of the structure and then using that instead of the raw atom positions. So by looking into how effective this is in grain boundaries, it can imply how effective it will be in other microstructures.
How did you choose the specific machine learning model used in your workflow?
So at present, we actually haven't locked in on a specific machine learning architecture. That is still being refined. Right now, the leading candidate is a physics-informed deep learning model This means that there are many layers of abstraction that the data goes through before a concrete result is found. This allows the machine learning model to investigate many nonlinear effects, which is something that we know is there from the research. And then the physics-informed component means that the end result will be governed by physical rules. And so it is much more likely to converge on a realistic solution.
What are some of the advantages to using a single material system, and why did you choose a copper-silver system in particular?
So choosing a single system instead of a combination of systems allows the machine learning model the best chance at learning the actual effects of the grain boundary instead of the effects of different elements. And it allows us to spend more time gathering more data from different types of grain boundaries instead of trying to make sure the different elements are balanced. The copper-silver system was chosen simply because it has the most data available. It is very commonly studied in material science, and so I was able to have a great head start in training my data.